All right, welcome everybody. So today we are exploring the fundamentals of AWS networking. This is a 200-level session, so we won't be diving too deep into any crazy architectures. But I firmly believe that once you have a good grasp of the fundamentals of networking, you can easily build those complex architectures. So you might be new to AWS. You're learning about it. You must have heard of Amazon EC2 instances, maybe RDS, managed database platform from AWS, or you want to dive deep into data analytics and you want to build Amazon EMR clusters, and many more such services. But today we won't be talking about any of these. We'll be talking about the underlying network infrastructure where you can securely launch these resources and scale them. So let's begin. In AWS, you have a region. Inside that, you create a VPC. You have subnets. You create instances into subnets. You have a route table based on which you route traffic. You have a public subnet, private subnet. Public subnet has access to the internet. We add a route for that. For the private subnets, we create a NAT gateway, route traffic via that. And you probably want to use the managed AWS NAT gateway. Now, to securely access AWS services, you have VPC endpoints. So let's create that. To access your on-premises networks, we have VPN, we have Direct Connect. You want to scale and talk to other VPCs, we have VPC peering. And finally, we have Transit Gateway, new release to connect thousands of VPCs together. Then we also have private link to securely access resources in remote VPCs, as well as AWS services. We have VPC flow logs for logs and monitoring. Finally, we have global accelerator for globally distributed workloads. All that made sense? Well, that was the agenda for today's session. So what we're going to do is we're going to dive deep into this architecture, look at various subcomponents, look at the fundamentals, try and understand everything, and finally, we'll come back to this at the end of the session. And at that time, if all of this makes sense, that's a well-spent 1 hour for both of us. So let's begin with VPC concepts and fundamentals. What's a VPC? A VPC is a layer 3 virtual network, which provides you a logically isolated section inside AWS where you securely deploy your workloads, your applications. That's all it is, a layer 3 virtual network. Let's look at the various fundamental concepts, starting with IP addressing. Now, when you create a VPC, you need to choose an IP range. This can be any IP address from the IPv4 CIDR range. But since a VPC is a private network, it's recommended you use RFC 1918 addresses because they were designed for such a use case for private LAN networks, which a VPC is. Now, IP addressing might seem very trivial. Hey, I know IP addressing. It's fundamental. I know what I'm doing. But what I see is when I talk to customers and they're facing problems with their complex architectures, the number one culprit is bad IP addressing scheme. So I want to share some tips and tricks, things to keep in mind. Number one, very simple, avoid overlapping IP addresses between VPCs and VPCs in your on-prem network. It's a lot of complexity when you're trying to run these complex NAT architectures to somehow make overlapping IP addresses talk to each other. Size your VPC appropriately. Don't have VPCs which are too large and you're wasting a lot of IP address space. At the same time, don't make them too small that you run out of it. But if you do run out of IP address space, we do have an option to expand and add more CIDRs to your VPC. So there is some hope there. And finally, if you have the ability to summarize the VPC's IP address range into a big subset, that's a big bonus. And what I mean by this is if you have 10 VPCs and you can say, hey, all my 10 VPCs belong to this big CIDR range, that's very helpful. And we will talk about one architecture later in the slide when we talk about Transit Gateway, where this will be very helpful. Now, when you create a VPC, you are spanning the entire AWS region. So for those who are not familiar with regions and availability zones, the AWS physical infrastructure is divided into regions, which is distinct geographic locations like US East, West, Island. And then you have availability zones, which are fault-tolerant isolated sections inside the region. When you create a VPC, it spans the entire region, right? So multiple data centers, multiple AZs. But when you create subnets inside your VPC, it maps to availability zone. Now, this is very important for you to understand because you want to deploy your workloads into multiple AZs for high availability, fault tolerance. So when you're designing your VPC and your subnets, keep in mind you just cannot have one subnet. You need multiple subnets which spans across AZs so that you can deploy your applications in them. Right? So just keep this in mind in your whole subnet planning phase. Subnet gets IP range from a subset of the VPC CIDR range. So here we have .0.1.2/24. Now you can also add IPv6 addresses to your VPC. So you can have a dual stack running both IPv4 and v6. The CIDR ranges is fixed. So you have /56 for VPC and /64 for the subnets. So let's just add IPv6 to this diagram for yep, and then it can be expanded, right? Okay, so we have assigned IP addresses to a VPC. Now, how do we route traffic between instances in a VPC and out? So each subnet has a route table, and this route table decides how traffic will flow within the VPC and outside. So let's look at an example, a screenshot of what a route table looks like. So every route table has a default route, which is the route number 1, which says 192.168.0.0/16, which is my VPC CIDR range, and target is local. All it says is any instances, any resources within a VPC can communicate with each other. You cannot delete this route. It's a default route which is in every route table. Apart from that, you can add additional routes. So we have a route to the internet, 0000 next hop IGW. And also a route to peering connection. So we'll talk about internet gateway, VPC peering. It will all make more sense. But this is how you add routes to your VPC's subnet route table. Let's talk about DNS. VPC has an inbuilt DNS. We call it the VPC DNS. It's powered by Amazon Route 53 service. But by default, it's not enabled. So you have VPC-specific parameters which you need to enable for DNS resolution and DNS host names. So when you enable DNS resolution, the VPC's DNS server becomes active and will perform DNS resolution. If you enable DNS host names, the EC2 instances which you launch in your VPC automatically get a DNS name, right? Now, if you want to have a custom domain name for your resources, you can create what's called a Route 53 private hosted zone and add entries in there for your host names and which maps to IP addresses of your EC2 instances. So here you can see an example. We have a record for example.demohostedzone.org mapping to IP address inside your VPC. And once you create that, the VPC's DNS can resolve this DNS record. What about on-premises? If you want traffic, DNS traffic coming from on-premises to be able to make it to the VPC's DNS, you need to use Route 53 resolver. Route 53 resolver lets you create multiple endpoints, an inbound endpoint and an outbound endpoint. In your on-premises DNS server, you'll create a forwarding entry saying anything which is for the AWS domain name, the next hop is the inbound endpoint. Similarly, for traffic which has to go back on-prem for your on-prem domain name, you create a forwarding rule in the Route 53 resolver console saying for these domain names, my next hop is the outbound endpoint. And then outbound endpoint can send the traffic out to your on-premises DNS server. Right? Fairly straightforward, inbound for incoming DNS, outbound for outgoing ADNS. And all of this is still using Route 53 and private hosted zones and then fully highly available managed DNS infrastructure from AWS. Let's talk about network security. So here we have 3 concepts, starting with security groups. So security groups are layer 4, fully managed stateful firewalls for your resources inside the VPC. It's an instance level resource. So every EC2 instance which you bring up, in fact, every network interface on your EC2 instance gets its own firewall. You define rules in the security groups, and based on those rules, the firewall will allow or block traffic. Let's try to understand with an example. Let's say you have your web fleet and your app fleet. We'll create a security group, tag it to all the instances in the web fleet, another security group, and tag it to all the instances in the app fleet. We write a rule on the my web server security group saying, allow all traffic from the internet on port 80. Right? Very standard HTTP traffic rule. And on the application side, we'll write a rule saying, allow all traffic, but we don't specify an IP here. We specify a security group and say, allow all traffic coming from my web servers. This is unique to AWS because this is called security group referencing, where you can allow traffic from another security group instead of IP. And you might say, why do I need to do that? I know my IP addresses of my web servers. Let's just use IP. That's true for most cases. For several cases where you're using auto-scaling and you bring up and bring down instances dynamically, IP addresses come and go. You cannot keep updating your security groups with new IP addresses and keep deleting IP addresses. You might say, hey, I'll just allow it for the entire subnet. That's fine, but that's too permissive. Using security group referencing, you can be exact and allow traffic only from those instances which is tagged by a given security group. So this is a best practice which we recommend you use. So let's look at a screenshot on how security groups look. So here we have a security group which allows HTTP traffic from anywhere, both IPv4 and IPv6. And then the app security group looks like this. TCP port 2345 is allowed from a source, which is another security group. Next, we have network access control list, NACLs. Now, network access control lists are a little bit similar to security groups, but with few key differences. And let's talk about them. I'm not going to cover all of them, but the top 3. Security groups operates at an instance level, actually, to be more specific, ENI level, while network ACL operates at a subnet level. Right? So any traffic which is incoming into the subnet or exiting the subnet will be blocked or allowed using the network ACL. Security groups supports implicit deny, and you have to write allow rules. With network ACLs, you can do both, implicit deny or implicit allow. The main one is security group is stateful. So return traffic is automatically allowed because we are doing connection tracking. We are monitoring the TCP connections. With network ACLs, that's not the case. We are not tracking any connections, so the return traffic has to be explicitly allowed. So in that sense, if you see, security group is a little easier to write and manage when compared to network ACLs. Now, we have a security groups, firewalls defined. How do I get visibility into what traffic was allowed, what was denied, what's flowing? Give me some visibility. And that's where the flow logs come in. VPC flow logs gives you visibility into the traffic inside your VPC. You can use it to troubleshoot what's happening. So if you're trying to access an EC2 instance, some resource, and you're not able to, your connection is getting dropped, you can look at security groups, VPC flow logs. And a lot of times, it's just overly restrictive security groups which is causing the problem. And finally, you can do traffic analysis. You can push these VPC flow logs to an S3 bucket or to Amazon CloudWatch logs, then later ingest these logs into your analytical tool, whether it's Hadoop-based or you can use Amazon CloudWatch log insights. and perform an analysis of the traffic. So you can figure out, hey, I'm getting a lot of traffic on this port from this source, and it's all getting denied. What is this source? And it might be like a blacklisted IP, something like that. So you can do an analysis of your traffic. So if you go to the VPC dashboard, click on a VPC, there's a column there called flow logs, and that's where you create your flow log. You specify whether you want to push it to S3 or CloudWatch or both. So how does the flow log format look like? So you have an AWS account, source IP, source port, protocol, packets, accept or reject. Now just keep in mind that this is not a packet capture, and this does not show you a line item for each and every packet. This is for a flow. So we are monitoring flows, and we are giving you flow information here on what was accepted, rejected. OK, so I think we have an understanding of what a VPC is, how routing works, DNS, subnets, security. Now let's talk about connectivity options. By default, when you create a VPC, you cannot send traffic into the VPC or outside the VPC. VPC is completely isolated. Only resources inside the VPC can talk to each other. So you explicitly have to allow connectivity outside the VPC. So let's look at which destinations can you reach and how do you do that. So we have internet connectivity or not. You might or might not want to expose your applications to the internet. If you don't want to expose your applications to the internet, whatever we talk about in this section, just don't do that. Connecting to other VPCs, so that's critical because you spin up multiple VPCs, you want them communicating to each other, as well as to your on-premises network. I think hybrid cloud setups is a real thing, and you want your data centers to be an extension of Amazon VPC, Amazon network, so let's bring them all together, and we'll see how that can be done. So internet connectivity. You have your resources inside your VPC in subnets. You have your route tables, which has just the default local route. Now, to enable internet connectivity, you need to create and attach an internet gateway. An internet gateway is a fully managed AWS gateway which provides internet connectivity, no bandwidth restrictions, no single points of failure. You add a static route in your route table saying, for all my default traffic outside the VPC, my next hop is internet gateway, right? So step 1, create an attached internet gateway. Step 2, add a route. Step 3 is where you attach an elastic IP to your instance. For internet connectivity, the source traffic has to come from a public IP, and that's what we're doing here. Now, if you see, I mentioned, hey, put your EIP onto the instance, but in the diagram, I put it on the internet gateway. And that's because when you attach an elastic IP or a public IP to your instance, what's happening behind the scenes is internet gateway is creating a NAT rule where it will take the packet coming from instance A and source NAT to the public IP. So if you go to the instance A and do if config or IP config, you won't see the public IP there. It's actually a NAT which is done on internet gateway. So you send traffic to the internet gateway, and the internet gateway can send traffic to AWS resources, which are outside your VPC realm, which are addressable by public IPs, as well as the internet. And we call this subnet the public subnet just because it has access to the public internet. Now, you might be thinking, hey, those AWS resources, S3 Dynamo, they are inside the AWS region, but still you're using internet gateway to reach them. What's the deal here? And just hold that thought, and we'll come back to that later in the presentation when we talk about VPC endpoints. Now, for some instances, you don't want them to be exposed to the internet. You want to firewall them off using like a DMZ architecture. So you can put them behind a NAT. Using VPC route tables, you can put an EC2 instance in line for all your outbound traffic. So as you can see in the route table of the subnet below the public subnet, we have a route saying all default traffic goes to next hop instance B. And that's where we'll configure source NAT rules. We'll attach an EIP to instance B, send all traffic to instance B, which does the source NAT, sends it off to internet. and all return traffic flows via the instance B. So essentially, your instance B becomes DMZ, where you can put firewall rules, and your instance C is in a private network. Now, you don't want to get into the business of managing NAT gateways, do you? Right? So that's where AWS released the fully managed, highly scalable managed NAT gateway. So you can use that. Works in a very similar way. You put a subnet entry saying next hop, NAT gateway. And all the traffic goes to NAT gateway, and we send it off to the internet. And you don't have to worry about managing a NAT infrastructure. Now, this subnet, since it's totally private, isn't exposed to the internet. We call it the private subnet. So this was connecting to the internet. How about connecting to other VPCs? And that's where VPC peering comes in. VPC peering is the most simplest and straightforward way of connecting two VPCs. You have VPC A, VPC B. You want to connect them. Oh, we also have C and D. We should not forget about them. You want to connect them, we just do the peering. More peering, and then more peering. Right? So you get an idea. It's a full mesh connectivity. So any VPC you want to connect to, you need to create a peering connection between them. But what VPC peering gives you is full IP connectivity. This is critical to understand. You connect two VPCs together. Any IP address in VPC A can talk to any IP address in VPC B. Yes, you need to have routes in place. Security groups, network ACLs can block. But from a routing perspective, it's full IP connectivity and routing. You can do VPC peering across regions, as well as these VPCs can be in different AWS accounts. When you're doing VPC peering across regions, it's all through Amazon backbone. It's fully encrypted. Right? So we are taking all of that undifferentiated heavy lifting for you of providing connectivity between our regions. VPC CIDR ranges must not overlap, otherwise you cannot peer them together. How does VPC peering work or get established? Step 1, you initiate a peering request. Step 2, you accept the request. And finally, you create routes. So this is an example how the routing table looks like. So we have a destination, 105500, that's my peered VPC. And my next hop is a peering gateway. Right? So when you initiate a connection, and accept one, this peering gateway gets created behind the scenes for you. And then you can just send traffic to this peering gateway. So VPC peering is fine. But we just saw it's a full mesh. And when you have hundreds of VPCs, even tens of VPC, the full mesh can get a little complicated. Let's see why. So we have two VPCs. We peer them. Two more VPCs, peer them, full mesh. Now we want to connect on-premises networks to these VPCs. It's a VPN connection per VPC. Now we have Direct Connect, and now we have to create more connections, more connections, more connections. And all of these connections become difficult to manage. At scale, this is just 5 VPCs. Just try drawing this architecture for 50 VPCs. It's crazy. And we do realize that. And that's why we released the Transit Gateway, which solves this problem with a different design topology. No more full mesh. Let's jump to hub and spoke. So now we have VPCs. We put a transit gateway in middle, which becomes our hub. And all these spoke networks just connect to the hub. If you want VPN, just VPN into the hub, and you get connectivity to all the VPCs. How about Direct Connect? The same thing. Just create a Direct Connect to the transit gateway, and you get connectivity to all the remote networks it's connected to. If you're thinking what a Direct Connect is, we are going to cover that, so just hold that thought. Transit gateway is critical. So I want to dive a little deep into what a transit gateway is, how it works, so that you leave here with a good understanding of it and can get started very easily. So here we have 3 VPCs, VPC A, B, C, and an on-premises network. And we connect all of this to the transit gateway. Connecting a VPC to the transit gateway is a native attachment. It's an API call saying, hey, attach my VPC to transit gateway. Done. For on-premises network, you have VPN, and you also have Direct Connect. And we'll jump into a little bit deeper into that in the later slides. In your VPC subnet route table, you'll add an entry, a static entry saying, my next hop is Transit Gateway. So you basically send all the traffic to Transit Gateway, and Transit Gateway will route the traffic based on the destination. Transit Gateway has its own route table where it knows exactly where each and every network is and how to reach it. So here you say it has VPC A accessible through attachment 1, VPC B accessible through attachment 2, C attachment 3, and finally on-premises through VPN. Right? So send traffic to Transit Gateway, it knows where to send the traffic and how to send it. Now where Transit Gateway is really powerful is you can have multiple route tables. So let's do one thing. Let's split the route tables into two, and route table 1 has VPC A and B information, and route table 2 has VPC C and on-prem information. So what happens now is we are going to associate VPC A and B to route table 1, C and on-premises to route table 2. Once you do that, A can talk to B, C can talk to on-prem, but they cannot talk to each other. So A cannot talk to C and A cannot talk to on-prem, because now you have isolated them. If I want to draw an analogy, it's very similar to the VRF concept you have in on-prem routers. So we spoke about some terms, so let's see what they were. I talked about attachment. Attachment is fairly simple. It's how you connect Transit Gateway to a remote network. And that connectivity is called an attachment. Association, so you associate these remote networks to a route table, and that route table will be used to make any routing decisions for traffic coming from that remote network. And finally, propagation. Transit Gateway has its route tables, and it'll have a bunch of routes in there. You don't want to go and start writing routes statically. It's a lot of work. So to enable dynamic propagation, so that the Transit Gateway can learn all the CIDR ranges of the remote network it's connected to, you can enable propagation into route tables. So I'm getting a vibe from the room here that it's still not 100% clear what's this association propagation. So let's look at one example and solidify the concepts. So we have a Transit Gateway, and we have one route table 1. We're going to create a VPC llama. We are going to attach that VPC to the Transit Gateway. The attachment is called X. We're going to associate that to the route table 1. We're going to enable propagation, and once you do that, the CIDR range 10.100/16 is automatically learned by the Transit Gateway and pushed into route table 1. We have VPC Pegasus. Attach it. We call it attachment Y. We associate this to route table 1, enable propagation, and the route is learned. Same goes for Barry. And if you're wondering where these names came from, these are all unicorn names. Then we have attachment Z. Same thing, associate, propagate, routes learned. In the VPC subnet route table for Llama, we put a route saying my default gateway is Transit Gateway. So send all traffic to Transit Gateway, which is not for my VPC. Now, many of you might be thinking, hey, a few slides back he said when using internet, my default gateway should be an internet gateway, and now it's Transit Gateway. How does that work? So let's bring up an internet gateway. And the route table says next hop IGW, or the internet gateway. So now what happens? So in this case, you'll have to write a more specific route. And this is where if you could summarize your VPC CIDR ranges into one big CIDR, that's an advantage. Because now you can say, hey, I know all my VPC CIDR ranges belong to 10.0/8, so I'll just write a route saying 10.0/8 to Transit Gateway, everything else to the internet gateway. Right? This would not have been possible if your VPC CIDRs were not in alignment, and they were all spread all across. Perfect. Now, I also mentioned that VPC CIDR ranges can expand. So here I had just one. What if I run out of IP addresses in Llama VPC and I add additional ones? What happens? Well, since dynamic propagation is enabled, automatically those routes make it to the Transit Gateway route table. So you see those route got added. Now, the power of Transit Gateway is you can manipulate these routes. So you don't have to always use propagation. You can turn propagation off. You can delete routes. You can add static routes. You can do a whole bunch of stuff. So let's see an example. So let's turn off the propagation from Llama VPC, right? Once we do that, all the routes learned from Llama VPC disappear. Now, we'll add static routes. So we get the same functionality, but we are statically adding routes. And you might think, hey, why do this extra effort? Let's talk about a scenario where 10.900/16 is a CIDR range which I don't want anybody to reach. It's only for some critical workloads within the Llama VPC, and I don't want Pegasus, Barry, or anyone else reaching it. So what we do, we just delete it from the Transit Gateway route table. And no remote networks can now reach that route, that particular CIDR range inside the Llama VPC, right? So this is just a very simple example of how Transit Gateway works. You can create multiple route tables. You can isolate them. You can delete routes. You can add black hole routes and a bunch of other stuff. I have a link in there if you want to read more about it. So how does the console look? You go to the VPC dashboard, click on Transit Gateway, say Create Transit Gateway. And you have a bunch of options to fill out, name, description. You have an option of enabling VPN ECMP, which basically means if you want to create VPN connections to your on-prem networks, you can have multiple VPN connections and do equal cost multipath load balancing over them. You enable or disable default propagation of routes into the default route table. Generally, I recommend you disable this and create new route tables. Don't use the VPC's default route table. Transit Gateway's default route table. And you create it. Once you do, it shows up in the Transit Gateway console. Fairly straightforward. Now let's talk about some limits. The maximum number of Transit Gateway attachments per VPC is 5, and the total number of Transit Gateways per account is 5 as well. The important one is the bandwidth. You can get up to 50 gigs per second of burstable throughput per attachment. But for VPN, it's 1.25 gigs. But you can do ECMP and create multiple tunnels and hit that 50 gigs per second if you want. So you can have, if I do the maths correct, it's around 30 or so VPN tunnels, and you can get full 50 gigs per second of VPN throughput, because 50 gigs per second is the maximum burstable throughput per attachment. Routes per Transit Gateway, 10,000. That's huge. That's huge if you have a little bit history on what the limits previously were. This is a great news. And it can attach to up to 5,000 remote networks. So you can have 5,000 VPCs attached to a Transit Gateway and write all kinds of routing configuration in there and really create those complex architectures. What about cross-region connectivity? Transit Gateway is a regional resource. 2 Transit Gateways in remote regions cannot communicate with each other. There's no VPC peering-like functionality. But good news is we have already announced that we'll be coming up with this functionality. So later this year, 2 Transit Gateways in remote regions will be able to peer and talk to each other. If you want to go a little deep into Transit Gateway and the detailed information, this is a link in the slide deck. You can take a photo, or when the slide gets available, you can follow this link and get more information. OK, so far we have been talking about VPCs and connecting them. Let's dive a little deeper into on-premises networks and how you connect them to this VPC infrastructure. We briefly talked about VPN, but let's just recap on how you can set up VPN connectivity to AWS. So there are multiple ways. The most straightforward way, or the traditional way, is to create a virtual private gateway. A virtual private gateway is a fully managed VPN endpoint at the AWS end. You create it, attach it to a VPC. Very similar to how you create an internet gateway, attach it to a VPC. You create a virtual private gateway, attach it to a VPC. At your end, you have a customer gateway. It's just a representation of a VPN termination device on your data center. And you create an IPsec tunnel between them. So this is IPsec tunnel over the internet between the virtual private gateway and your on-premises network. You see we have two tunnels there. That's for high availability. When you create a VPN endpoint at the AWS end, we give out two IP addresses in different availability zones for HA. So you need to create two VPN tunnels. That's great, but with this model, you need to create a VPN per VPC. So if you want to connect to 100 VPCs, you need to create 100 into 200 VPN tunnels, not scalable. And that's where Transit Gateway comes in. So you create a pair of VPN tunnels to Transit Gateway, and Transit Gateway behind the scenes attaches to all these hundreds of VPCs, and now you get VPN access to the entire infrastructure. So again, going away from the full mesh model into this hub and spoke. If you already have site-to-site VPN running and you want to migrate away from that model to the Transit Gateway design, we have detailed instructions on how you can do that. We also have a second type of VPN endpoint. It's called client VPN. So till now, we were talking about site-to-site VPN. In a client VPN, you have a client. It's a mobile device, a laptop, and you want to connect that to your VPC infrastructure. So you can do that. So you set up a VPN to the client VPN endpoint. This client VPN endpoint attaches to the VPC and gives you access to the resources in the VPC. All you need is an OpenVPN compatible client. You create this TLS-based tunnel over the internet, attach the VPN endpoint to the VPC, and you get access to the VPC and all the different resources attached to it. Right, so this is really powerful because you can, if your VPC is connected to the internet, to other on-premises networks, the client VPN endpoint gives you the access to all those remote networks. Let's talk about Direct Connect. We were talking about VPN that's over the internet, that's fine, but for your critical production workloads, you need something more consistent. And that's where Direct Connect comes in because it provides that dedicated fiber connectivity between your data centers and AWS. So let's see how that works. You have on-premises network and you have the AWS region. In that, you have VPC and some resources sitting outside it, which have the public IP ranges, like S3. Now, in order to connect to AWS, you have to connect to us via an AWS Direct Connect location. This is a third-party co-location facility where we have presence. So AWS has cage and network equipment in there. You might have a cage in there as well, or you might come via a partner. Either ways, you have to establish connectivity from your on-premises data center to this third-party co-location facility, like the Equinix, core sites, and then initiate a cross-connect between your or a partner router to the AWS cage. Once this cross-connect is completed, your physical connectivity is done. Now, you need to get access to the AWS resources. To do that, there are a few ways. Number one, you can use the virtual private gateway, which we just talked about, which is a fully managed VPN endpoint. It also does Direct Connect. You create a private virtual interface to this virtual private gateway. Private virtual interface is fairly straightforward. You specify a VLAN ID, and you have to tag all the packets using this VLAN. You specify BGP parameters. This will allow the BGP sessions to come up and the routes to be exchanged between the virtual private gateway and your on-prem router. You also create a public WIF. Public WIF is a similar BGP peering setup. It's a different VLAN, and you can access AWS public services like S3, DynamoDB over this virtual interface. Now, if you had more VPCs, you have to create more virtual interfaces. Again, this is sort of a full mesh kind of a design where it's one-to-one mapping. Not scalable. You have hundreds of VPCs. You don't want to create 100 VLANs, 100 BGP peerings. So we bring in the AWS Direct Connect Gateway. AWS Direct Connect Gateway connects to multiple VPCs. So now, all you need to do is create a private WIF to a Direct Connect Gateway, and you get access to all the VPCs behind it. Additionally, you can access VPCs in any AWS global region using Direct Connect Gateway. So Direct Connect Gateway is a global entity, and it lets you access VPCs across AWS regions. This is new, and it's only possible with Direct Connect Gateway. So one WIF, many VPCs across regions. Not only that, you can also access VPCs across accounts. So this is new. If you're not familiar, multi-account Direct Connect Gateway now lets you create a private virtual interface to a Direct Connect, which can connect to multiple VPCs in different AWS accounts. Now, Direct Connect Gateway is fine, but it allows connectivity to up to 9 VPCs. I know what you're thinking. I just talked about Transit Gateway and the fact that it can connect to 5,000 VPCs. Show me a design where I can connect my on-prem network to 5,000 VPCs. And that's where Transit Gateway comes in. So you create a transit WIF to the Direct Connect Gateway. And instead of connecting the Direct Connect Gateway to your VPCs, Transit Gateway comes in. And so you connect to the Transit Gateway, and then the Transit Gateway connects to the VPCs. So to learn more about how Transit Gateway integrates with Direct Connect, I won't be going into further details, but there's a link which has all the fun information in there. Also, something new which we had released this year was support for partner connection speeds of greater than 1 gig. So if you want to come via partner, so you go to something like Equinix, Cloud Exchange, or the Verizons or AT&Ts, you can tell them, hey, I want Direct Connect circuit of 2 gigs, 5 gigs, 10 gigs. Before this, we only supported sub 1 gig speeds. Awesome. So before we wrap up, there are a few more concepts which I want to cover. And there is more AWS networking. So there's VPC sharing, VPC endpoints, and the global accelerator. So let's start with VPC sharing. So before VPC sharing, VPC was a construct which was confined to an AWS account. So if you have 2 different AWS accounts, you had to create a VPC per account. You cannot share a VPC across accounts. After VPC sharing, you can exactly do that. So let's try and understand this with an example and why you want to do that. Some advantages. So let's say you had your dev and test accounts and a bunch of production accounts. Fairly standard for any customer building AWS infrastructure. You have dev, test, production accounts. Now, since before VPC sharing, VPC was a resource confined to an account, so you have to create 1 VPC in every account. You have resources in them, RDS instances, Redshift cluster, EC2 instances, and even serverless Lambda functions. But you had the requirement where my dev and test environments should be able to talk to each other, and my production environments, the networking construct, network security of all of them are fairly similar, and I want them to talk to each other. Now, to enable this, you need to create Transit Gateway, VPC peering, and all of that. But your fundamental requirement behind building these accounts was user isolation, segregation, security at an account level. So after VPC sharing, what you can do is just have 2 VPCs. So here we have a dev test VPC and a production VPC, right? And within that, you can have multiple accounts share those VPCs. So Llama, Pegasus, Steve, and Iguana can go ahead and launch their resources in this shared production VPC, and all of these resources can talk to each other. Now, there are some terminologies which you need to understand when it comes to VPC sharing. So we have the concept of owner and participant. Owner, very straightforward, is responsible for creating, managing, deleting all VPC level constructs. So if you're creating subnets, routing, all of that is managed by the VPC owner. And the VPC participant is responsible for creating, managing the AWS resources, like EC2 instances, Redshift clusters, Lambda functions, all of that. VPC owner cannot modify participant resources, and VPC participants cannot modify VPC level constructs. Why use why use Amazon VPC sharing? A lot of reasons. Number one, preserve IP space. You might not think of this now, but when you are creating VPCs at scale and you're creating hundreds of VPCs, there is a lot of IP wastage. There might be some VPCs which will be underutilized. So having this larger VPC lets you preserve more IPs. You remove the complexity of having hundreds of VPCs, so we know VPC peering, no transit gateway, or at least less of that. So a much simpler network design. Separation of duties, this is a big one. A lot of customers said, hey, I want my networking team to manage the VPCs, and that's not something which my application owner should be bothered with. So perfect. The VPC, shared VPC is managed by the networking team, and the application owners can just go and deploy their workloads in subnets. And since you're using multiple accounts, you get the billing and user access isolation. Additionally, if they're all in the same AZ, there's no data transfer charges. Now, a lot of customers ask, hey, is VPC sharing something which I should always do, or is it VPC level segregation? And my answer is there's always a happy medium with these questions. You cannot just create one big shared VPC and put everything in there. Plus, at the same time, you cannot be creating thousands of VPCs. That does not scale. There has to be a happy medium. Try to build multiple shared VPCs based on sort of what you're trying to do. If you have applications which have similar networking requirements, putting them in a shared VPC makes sense. But if you want to create that network isolation between different applications, they have different routing requirements, then maybe put them in different VPCs. So it's a sort of a design decision there. More details on VPC sharing, it's link there. Cool. VPC endpoints. So when we were talking about the internet gateway, I said, hey, internet gateway, use this to access public resources in the internet, as well as AWS endpoints, which have public IPs. And for those who are not familiar, AWS has a bunch of services, and few sit inside the VPC and get private IP addresses like RDS, EC2. And there are some which sits outside the VPC, like Amazon S3, which is only addressable by public IP ranges. VPC endpoints let you access those AWS public services in a very private manner. So you don't have to traverse through the internet or use the internet gateway. And I don't know if you know this, but even if you're using the internet gateway, the traffic does not leave the AWS region. It's just a construct, but it stays within the region. So we have two kinds of VPC endpoints. We have gateway endpoints, interface endpoints, and it's also private link. We'll talk about that. So let's talk about gateway VPC endpoints. Gateway VPC endpoints is similar to an internet gateway. You create the VPC endpoint gateway and attach it to your VPC. You have to create a route table entry saying my next hop is S3, right? So you use a prefix list, just something which is made available to you once you create the endpoint. And that's the destination. My next hop is the gateway VPC endpoint, right? Critical thing to keep in mind, you are still accessing the AWS service, which is S3 in this case, using its public IP. But behind the scenes, what we are doing is we are taking that traffic, which is destined to a public IP, without the need of an EIP, routing it privately through the VPC endpoint. So you don't need an internet gateway, you don't need EIPs. You can just privately route traffic via the VPC endpoint, but the destination CIDR range is still a public IP. And the same goes for the private subnet as well. Now, this gateway VPC endpoint is today available only for two AWS services, Amazon S3 and DynamoDB. And that's why you see here an example. The public subnet has a route for S3, and the private subnet has a route for prefix list. So let's just get rid of our internet to avoid any confusion. So you want to access S3 DynamoDB privately, this is your architecture. No internet gateway required, no public IP required. Now, the second type of VPC endpoint is called the interface VPC endpoint. And this gives you access to a lot more AWS services. The way this endpoint works is fundamentally different from gateway VPC endpoints. While gateway VPC endpoint was a gateway, this private endpoint shows up as an ENI in your VPC. This ENI has a private IP address. You can access this private IP to get access to the AWS public IP endpoints. So they are not public anymore. They become private. They become part of your VPC. With gateway VPC endpoints, they were still public. We were finding a way to route traffic to them privately. With this, we are bringing it into your VPC. The public the public DNS of this public endpoints now map to a private IP. So as I said, it's fundamentally different on how you access these services. You don't need any special routing in there. You just need the default local route, which you cannot delete, because traffic is being sent to an ENI and IP inside your VPC. So when you go to the VPC endpoint dashboard, you can see you have a bunch of options there, some type gateway, some type interface, and you can select and create them. So you have gateway, and that's your interface. And finally, private link. So private link is a way for you to securely access resources in a VPC, but it's a little different from how VPC peering and Transit Gateway works. That was full IP to IT connectivity. This is not. This lets you expose only a service inside your VPC to a customer VPC. So let's say you're a service provider, and you have an application, software as a service, which you want to expose to the customer's VPC, but you don't want to expose the entire VPC and all the resources in that. You just want to expose this particular service, which is running on these 2 EC2 instances. So how do you do that? First, you create a network load balancer, point them to your resources you want to expose, create a private link, and what that does, it drops an ENI into the customer's VPC. Now, the customer can send traffic to this ENI, and it also has a DNS name. So that DNS name maps to the private IP of that ENI. So the customer, client, end users, hosts send traffic to this ENI, and behind the scenes, magically, we are sending that traffic to the network load balancer. There is no VPC peering. There is no transit gateway. 2 completely isolated VPCs, but using this technology, we are able to send traffic to the network load balancer. So these client endpoints in customer can only access that network load balancer and nothing else, right? So it's a different way of exposing your resources to other VPCs. It's very, very, very widely adopted in the service provider space. For example, Salesforce has this kind of functionality where you can access Salesforce public APIs privately through private link, and you don't have to go through the internet. Our final topic of the day, global accelerator. So all of this is great. I know you're getting excited. But you might want to deploy this infrastructure, this VPC infrastructure applications in multiple AWS regions and run them in an HA mode, right, or an active standby mode. If you want to do that before global accelerator, you had to rely on DNS. You create a DNS record, give it to your users across the globe. They hit this endpoint, and using a latency-based routing or geo-based routing, traffic is automatically sent to the right AWS region. This is a use case where you're running a workload in multiple regions, and it's all HA, highly available. Now, this is great, but has some challenges. Stale DNS cache, there's no fixed, consistent IP, and the main one is the end client hosts are sending traffic to these resources. Everything is going over the public internet. So if somebody is sitting in Singapore and they're trying to access something in Ireland, all the traffic from Singapore to Ireland is going over the public internet. We don't want that. We want you to be able to use the AWS backbone as much as possible so that we give you that consistent experience. So for that, we have enabled Global Accelerator, which gives you this edge locations which AWS has across the globe. And you get a static IP, a anycast IP, which you can give to your clients. Your clients can access your resources using this one single IP. Traffic will enter the AWS backbone through the nearest location. So instead of coming all the way from Singapore to Ireland over the internet, the user's traffic will get ingested into the edge location, which we have in Singapore. And from there to Ireland, it's all over AWS backbone. Much better consistency and performance. and now your users can access your AWS resources. We are doing health checks behind the scenes. We know exactly which is the nearest region. If you have resources running in Singapore and Mumbai, we'll send it to Mumbai. We won't send it to Ireland, right? So we know all of that latency-based routing is all done behind the scenes. So you get a global network. Applications can keep client state. It's very important. And you get static anycast IP. So if your clients require a single IP for firewalling and stuff, this is perfect. I think the next session in this room is on global accelerators. So if you're interested in this, stay tuned. James is a great speaker, and he'll be talking in more detail on how some of this works. OK, so let's bring everything back together. And now I hope this all makes sense. So we have VPC with instances in there. We talked about route tables is how you send traffic out. Their default route exists for every VPC. You want to talk to the internet? You create an internet gateway. Add a route pointing all default traffic to the internet gateway. Attach an EIP. Now, internet gateway is doing the source NAT for you. Send the traffic out. For your private applications, which you don't want to expose to the internet, you want to use a NAT gateway. Again, use routing tables, point all traffic to this NAT instance, and send it out. Use the AWS managed NAT gateway. Don't try to build your own NAT gateway. You want to access the AWS services sitting outside the VPC? Don't use internet gateway. Use VPC endpoints. We have two types of endpoints. We have gateway endpoints, interface endpoints. For the gateway endpoints, you need to add a route, S3 prefix list. Next hop is the VPC endpoint, the gateway endpoint. You want to talk to on-premises networks? You can use VPN. You can connect them directly to the virtual private gateway, or you can use Transit Gateway. You can use Direct Connect with the Direct Connect gateway to connect to multiple VPCs across AWS regions. Again, all of that requires routes to be added into your route table. So we're doing that on the side. If you want to connect to other VPCs, you can use VPC peering. We talked about that. Full mesh, VPC to VPC, one-to-one mapping. Is problematic at scale. So we have Transit Gateway, which creates this hub and spoke design. You can connect to thousands of VPCs. We also talked about private link interface endpoints, as well as where you can connect to resources and other VPCs through this private link service provider customer kind of an architecture, right? We talked about VPC flow logs. All of this traffic flow which is happening needs to get captured. You need to have visibility and analysis of what's happening in your VPC. So everything can be done through VPC flow logs. Send it to S3, ingest them in batch to do analysis, or send them to CloudWatch. Finally, if you want to set this all up in different AWS regions and enable high availability and provide low latency, consistent performance to your users who are distributed globally, all across the globe, use Global Accelerator. If you want to learn more, we also have a AWS Certified Advanced Networking official study guide. If you want to give a certification, get trained in this, it's a great book. I was lucky enough to be one of the authors. So it's a great book. We don't get any royalty if you buy this, so it's no self-promotion here. Thank you.